Yeah, stand by. The streaming is starting.
Okay. Well, let me know when.
All right, John, we are live on YouTube. Please, if you would, the introduction.
Yes. Good evening, everyone. Our guest speaker is Karina Alden. Karina Alden is a space weather analyst and outreach coordinator with the Moon, Mars.
We are live on YouTube. Sorry. Please, if you would, the introduction.
Yes. Good evening, everyone. Our guest speaker is Karina Alden. Karina Alden is a space weather analyst and outreach coordinator with the Moon.
Yeah, hold on a second.
We're gonna be stuck on a loop, though.
Oh my goodness! Oh my goodness! Oh my goodness!
Yeah, this is fun.
It's like sci-fi. I'll start whenever you tell me, Jim.
I think he had to mute himself to try and fix it. Would it be a presentation without
Go ahead, John.
Okay. Tonight's speaker is Karina Alden. Karina Alden is a space weather analyst and outreach coordinator with the Moon to Mars Space Weather Analysis Office at the Heliophysics Science Division at NASA's Goddard Space Flight Center. Everyone, welcome Karina Alden.
Thank you. Alrighty. So I will go ahead and believe you're still seeing my screen. So
yeah, hold on, Karina. Hold on, John.
NASA's Goddard Space Flight Center.
Yeah.
Everyone, welcome Karina Alden.
John, we're gonna do this again in just a minute, okay?
Well, I think we're doing it again.
Please stand by. Hold on 1 second, all right?
just take two.
Yeah. Hold on. All right, John. I promise. Go.
I'll make promises. Tonight's speaker is Karina Alden. Karina Alden is a space weather analyst and outreach coordinator with the Moon to Mars Space Weather Analysis Office in the Heliophysics Science Division at NASA's Goddard Space Flight Center. Everyone, welcome Karina Alden.
Thank you. So as mentioned, I am a space weather analyst and outreach coordinator, but I'm going to talk to you a little bit about what space weather is and how we analyze it. And so further ado, I did copy and paste my little intro about me. So if you missed it before, I am a space weather analyst and outreach coordinator with the Moon to Mars Space Weather Analysis Office, aka M2M SWAO, I guess is what we're calling it now, which is in the Heliophysics Science Division within the Space Weather Laboratory at NASA's Goddard Space Flight Center. And as part of this team, I have the pleasure of analyzing any eruptions from the sun, and I'm going to go over what all of those eruptions may look like. But I basically, when someone asks me, what do you do for work? I typically say, I stare safely at the sun. It's very important to say safely in support of NASA's human and robotics missions while also communicating the science with the public. So that's a little bit about me, but I wasn't always a space weather analyst. Prior to joining the Moon to Mars team, I grew up in Western Massachusetts, in the Berkshires, if you're familiar with it. Woohoo! It's a gorgeous area. It's a very, I would say, kind of empty. It's not too populated. So I basically grew up kind of in the boonies. I went to really small schools, so it gave me a lot of opportunity to explore different opportunities and what I wanted to do. As I was getting close to graduating high school, I thought that I would want to do astronomy. However, a conversation with my mom and looking at Google for jobs in astronomy, only one popped up in Australia, and she said, absolutely not. And so I ended up changing gears and looking at meteorology, so studying weather on Earth. However, when I got to college and I decided to go to a college in Vermont, it felt very much like home. It was called Linden State College. It's now called Northern Vermont University at Linden. Or actually, it's called Vermont State University at Linden. It's changed its name a couple times recently due to unifications. But I went to this beautiful college up in the Northeast Kingdom of Vermont and had the wonderful opportunity to study under some of these great professors. However, I quickly discovered that meteorology was not for me. I was not interested in terrestrial weather. It was more of a hobby for me rather than a passion to do in real time. But I did have the opportunity to attend a conference. And at this conference, there was a space weather section. And I thought, well, what's space weather? I got to know. And so I attended the whole week of learning about space weather, and I discovered that it was something I was really interested in. I didn't understand most of it. I just know that there was really pretty pictures of the sun, and I was intrigued. There was a lot of questions, a lot of unknowns, and I wanted to be part of the group of people solving the questions. And so I ended up doing 4 summer internships. The first one was at the National Solar Observatory when they were located in Sunspot, New Mexico. And I studied solar irradiance variations. So looking at spectral lines of the sun versus my summer internship after that, I was at Southwest Research Institute, which was located in Boulder, Colorado. And I spent a summer studying coronal mass ejections, which I'll get to tell you and show you a little bit more about what those are. And then I spent 2 summers at NASA's Goddard Space Flight Center, which is where I am now, each doing 2 different internships. So one was more about space weather impacts on Earth, and so looking at what was called ionospheric precipitation. And then the summer after that, I got to go back to looking at the sun and studied more about solar filaments, which we'll talk about as well. And so I had done all of that. And then I graduated college with a bachelor's in applied mathematics and minors in physics and atmospheric science. And I got into the real world, and I was hoping to take a gap year before doing grad school. And then grad school never ended up coming along because I ended up getting kind of scouted a little bit to join the Moon to Mars team. So through some networking that I had done, I actually was reached out to on Twitter via some Twitter DMs and ended up getting asked if I was still interested in doing space weather, because at the time I was helping people navigate student loan debt. So very different field. However, I was still pursuing space weather as an amateur space weather person. And I ended up getting to do an interview, and next thing I knew, I was part of the team. And so I now work at the Moon to Mars Space Weather Analysis Office, and I've been there since at least November of 2020. So this November will mark 4 years. And it's been with them ever since, which hasn't looked the same every day. So here's kind of what a day in the life may look like, however, depending on the day. So we've got some images from when I was assisting with outreach at the annular eclipse in Kerrville, Texas. So that was back in last October. A typical day in the office where I may be eating out of a giant box of goldfish so that I can fuel myself to stare at the sun longer. Doing some educational topics down in Ushuaia, Argentina. So I've kind of traveled all over the world with this job. I've had the opportunity to present at conferences. I've done even some live shots with NASA's in NASA's live studio, and then just doing regular analysis on the day-to-day. And so this is kind of what it looks like, but if I were to show you really what a day-to-day looks like, you'd probably need to know what exactly space weather is. And so what is space weather? Let's define it. If you Google the definition, you'll probably come across multiple definitions that all point to the same thing that state the sun and its relation to Earth. However, space weather stretches well beyond Earth, impacting missions and planets to the farthest points of our solar system. So space weather by definition is the relation of the sun's activity, interplanetary space, and all of its inhabitants. However, those inhabitants sometimes can feed back into the system, and that may be confusing. However, if you were to talk to any of the folks in the ionosphere, thermosphere, and mesosphere community, they'd probably tell you that there's that feedback system. However, we're not going to go into that because we have limited time. So we'll just focus on those aspects of how the sun touches everything and what I focus on as a space weather analyst with the Moon to Mars office. So this is kind of the umbrella of space weather. And so we're going to walk through a good chunk of these, possibly not every single thing, but we're going to try our best. So there's a lot of different eruptions when it comes to the sun. We've got solar flares, we've got filament and or prominence eruptions, we've got coronal holes, there's coronal mass ejections, there's solar energetic particles, and then closer to the Earth side of things, we've got arrival signatures, which we also look at other locations, which include some of our other spacecraft in the same orbit as Earth, but ahead of Earth, as well as at other planets like Mars. And then we have geomagnetic storms, which is Earth-based, and then we have a modeled magnetopause crossing, which I will get into that as well, but that is also Earth-based. So when it comes to solar flares, we monitor them using a satellite called the GOES satellite, which is one of NOAA's missions. And then we also monitor them through one of the satellites called the Solar Dynamics Observatory. So this image in the background, which I'm realizing this probably is covering it a little bit, but we have this very bright portion here. And what you're seeing in this bright spot here is actually the solar flare. So I'm pointing out in a timeline. So this plot is showing you basically the flux that's ingested from all of these bright eruptions on the sun from a satellite. So this plot is from the GOES satellite, and this image back here is from the Solar Dynamics Observatory. And so what you're seeing here is actually just a snapshot image of the flare that's happening here. And so a solar flare, as I should define it probably for you, is a sudden brightening observed over the sun's surface, or in this case, the solar limb, which is interpreted as a large energy release. Many flares are usually followed by mass ejections from the solar atmosphere called a coronal mass ejection, but they don't always have to produce a coronal mass ejection. If there is a coronal mass ejection, it can include electrons, ions, and atoms that will be pushed through the atmosphere of the sun, which is called the corona. And basically this big plume of cloud with all of these charged particles gets pushed through space and can impact missions. And so in this image, we're actually seeing what is called an X 1.5. And so you may be thinking, okay, how do we have this classification? What does X really mean? So if you look on the side here, there's actually lettering. And so we have classification of flares. We have A-class flares, which usually are all the time flares is how I like to call them. It actually doesn't have a name for it. B flares are your typical background flare. C-class flares are common, so we get these fairly commonly. M-class flares are considered major flares or moderate flares. And then X-class flares are extreme flares or very strong flares. And so in this case, this flare was produced as an X 1.5, and the value comes from how high the flux is here. And so A, B, C, M, and M-class flares all cap at the 10 mark. So basically, it's logarithmic. So you have you can have an A1 through a 9.99999 class flare, but if it were an A10, that wouldn't exist. because once it reaches A10, that's technically a B1 class flare. And then the same with C class flares and M class flares. However, with X class flares, kind of similarly to how we think about tornadoes and scaling tornadoes or scaling hurricanes, they have a cap of that fifth marking, right? So with tornadoes, they have the EF 1, 2, 3, 4, and 5. It doesn't matter how high the wind speeds may be for a tornado or for a hurricane. If it reaches category 5, there's nothing above that. So in this case, that's how it is with X class flares, is that there's nothing above it. And so with this, solar flares, as I mentioned, are often associated with coronal mass ejections, aka CMEs, but they can occur without producing a CME, and CMEs can also occur without a solar flare. So you might be wondering, how can a coronal mass ejection exist without a solar flare? Well, we have another cause of filaments and prominences. So in this case, we're actually seeing, and I'm trying to think if this is a video or not. I don't think, it might be. Nope. I don't think my video worked. Oh, darn, sorry. So in this case, we can see on the left, we have this lovely filament material here. So this is a filament / a prominence. So when they were first looking at, when astronauts were first, or sorry, not astronauts, when astronomers were first observing the sun through telescopes, they were seeing basically these dark marks on the sun. And then they were also seeing these bright marks on the limbs of the sun. So you can see these bright portions. And so they labeled these prominences, and then on the disk, they labeled these filaments. Well, the more we started observing the sun, we quickly learned that they are the same thing. And the reason they look different is because they look bright amongst the very dark background of space, but against the brightness of the sun, they end up looking very dark. And this is because it's very dense and cool material that is suspended along the magnetic field lines of the sun. And so we can't typically see magnetic field lines on the sun, but this does give us a clue of what those field lines may look like, thanks to the suspended plasma. So this cool gas and particles. And so let's see if I can go forward. I think that was another video that's sadly not going to work. So these, to give perspective to scale, are enormous. So as you can see here, Earth is just a tiny little dot compared to how large this filament could be. And when it does finally erupt, we can see those coronal mass ejections. And so these are some images to show that basically with this one, as it erupted, we ended up seeing this big plume of material coming from the sun. And then there was a filament erupting here, and we can see this giant plume as well coming from the sun. And this is what we have as the coronal mass ejection. And so we're going to look a little closer at this one here. And so we can see in this, and this is another spacecraft. This is all viewed from the SOHO spacecraft. So the SOHO spacecraft has two what are called coronagraphs. And basically what a coronagraph is it's an artificial eclipse. And so we have this disk called an occulting disk that gives that artificial eclipse look. And what it's doing is it's blocking out the brightest parts of the sun. So it's blocking out this disk that we can see here. And then we can get this occulting disk here. And basically what we're end up seeing is this white circle is showing where the sun actually is. And so we're blocking out even more than what the sun covers to make sure we're blocking out the brightest part of the sun, so we can see that what's typically more faint and more difficult to see, which is this coronal material from the sun's outermost layer of the atmosphere called the corona. And so this is a coronal mass ejection, and we can actually see there's very bright portions in here, and that's due to that filament that erupted with it. And then this is even further out in the field of view. So the sun, you can see perspective-wise how large it looks here compared to how small it looks here. And then an even larger occulting disk showing us how how incredibly large these coronal mass ejections are. And what my team gets to do is we get to try and measure these using a measuring tool. However, to give you an idea, so this is a video that should work. I tested this one out. We've got an image of the sun here, so you can see where it would usually cover from here or here. And then we've got these layered on top of each other. So I've got a layer of the SOHO C2 coronagraph and then the SOHO C3 coronagraph on the LASCO instrument. And then in the middle here, I've got an image of the sun from the Solar Dynamics Observatory, specifically the Atmospheric Imaging Assembly instrument. And basically what you're going to see here is a CME that we had back on June 8th of this year. And this CME was related to solar flaring. So we're going to see a little bit of a different looking CME. And I'm going to let that play through so you can see how large these eruptions are. This is a really large CME, or coronal mass ejection. And if you noticed, following the eruption, we suddenly started to have all of this particles in here. It kind of looks like snow in the coronagraph. And that is actually from the observing spacecraft getting saturated from the solar energetic particles that just erupted from that solar flare. And so that leads me to the next part, what we can measure, which is solar energetic particles. And this is in the environment near Earth. And so what you're seeing here is basically a very big plot of measured data of solar energetic particles, specifically protons. And so this is measured proton data. And we can see that there's all these different channels, but the main ones that we worry about at NASA is the greater than 10 MeV channel and the greater than 100 MeV channel when notifying NASA missions. And so these two, which are in the red line here, and the blue, this lighter blue or cyan color here, those two channels, when they cross specific thresholds, is when we would notify NASA missions to let them know that they're in a solar energetic particle event. And solar energetic particles are basically very important because they can cause damage to spacecrafts and can also increase radiation risk to astronauts. So this is really important for when we have astronauts on the ISS. This is also really important when we have astronauts as they are trying to go to the moon and eventually to Mars. And so here we can see that we did have, following the August events, I believe that this was this year, we had an increase, if not this year, then last year. We had this increase in the greater than 10 MeV channel, and then we had another event that caused an increase in the greater than 10 MeV channel, but not too much to disruption in the greater than 100 MeV channel.
I just want to confirm MeV is million electron volts.
Yes, thank you.
Okay.
Yep. So million electron volt or mega electron volt is what we have. And so with this, so SEPs usually occur when charged particles in the sun's atmosphere are accelerated to extreme high velocities. These charged particles, referred to as solar energetic particles, can escape into interplanetary space where they follow the interplanetary magnetic field. So just following the magnetic field lines that are in space, and then along the Earth's magnetic field lines. And then when solar energetic particles interact with the Earth's magnetosphere, they are guided to the Earth's magnetic field towards the north and south poles where they can penetrate into the upper atmosphere. However, us here on Earth, we don't really notice anything, and we don't really have anything to worry about. But this can be important with missions as well. And so this is another example where we had quite a large, and this is the June 8th event that I pointed out from earlier this year that had that beautiful large CME that we just saw in the video. This is where we can see we had a very quick event, a very energetic event. And so you could see that in the imagery, but now you're also seeing the data that shows how strong this event ended up being. And so with the previous event, we can see that this red line didn't really move at all. It moved very little, but then with this more recent event, we had a big jump. And so it was a very energetic event.
Karina,
Yes.
at what value would our satellites be impacted? Uh, Greater than 10 MeV? Is there a number that says
Yeah.
our
So,
satellite may be in jeopardy?
so I don't know about specific numbers for when they be in jeopardy. I know that when we notify for the greater than 10 MeV channel, we follow what the Space Weather Prediction Center at NOAA does. And so basically, they have guidance to do when it crosses the 10 PFU value here. So the proton flux unit here, that's when you would notify for a threshold crossing in the greater than 10 MeV. So that's that cyan color. So you can see here it very quickly crossed 10 PFU and was at nearly, I think, 1,000 at its peak. And then the greater than 100 MeV channel, which I believe they're more concerned of in terms of astronauts, but I'd have to double check that, is usually the 1 PFU threshold. So it crossed that as well and was almost at 10 PFU here. So very, very quickly crossed values here. But if we go back to this one, we can see that this event wasn't as strong. And so the cyan had only crossed, I'm sorry, I've been pointing on my other screen. You can't even see where I've been pointing. So the cyan color, the 10 MeV here, or the greater than 10 MeV crossed this 10 PFU threshold here, while the red stayed well below its 1 PFU threshold, versus if we go here, this greater than 100 MeV crossed the 1 PFU pretty quickly, and then this cyan color crossed the greater than 10 MeV threshold of 10 PFU pretty quickly as well. Hopefully that helped answer the question.
Thank you.
Mm-hmm. So another thing that we can see are coronal holes, and they probably sound scary because it sounds like there's a hole in the sun, but I promise you there's not. With coronal holes, it's basically this beautiful gap we see here, this dark region here within the solar corona, showing basically where the magnetic field lines on the sun don't quickly come back down to the sun. So basically there's escape in the atmosphere of the solar corona that's allowing all the material to come out, and so it causes this dark appearance to show in the imagery. And so what happens from that is that basically all of the material that's escaping from here causes a fast solar wind. And so a solar wind, when we look at this image here, which I apologize is probably very difficult to understand, but basically what you're looking at is you're looking at a top-down view of the solar system, and you're seeing some of the missions we notify here. And so in the middle here is the sun. This yellow dot here is Earth. And then we've got a bunch of other missions and other planets labeled here. But the important thing is to see that there's this spiral going on. And basically what you're seeing with this spiral is what's called the Parker spiral. And so because the sun is rotating, but it's constantly emitting a solar wind, which is basically just a stream of particles and material, we end up getting a spiral as it spins. If you think about it, the sun is kind of like if you were to put a string on a tennis ball and then you dunked it in water and you took it out of the water and you spun it and you watched all the water escape from the tennis ball. That's kind of what the sun is doing. The sun is the tennis ball, and as it's spinning, it's letting out all of this solar wind. And so we have slow solar wind when it's basically capped here. And then we also have fast solar wind, which comes from these coronal holes. And so with this coronal hole, we can actually model where we think we may get a high-speed stream. And so a high-speed stream at Earth is basically just when we have this solar wind, this fast solar wind, which usually isn't very dense material. It's pretty thin, but it's very, very fast. Like usually, in this case, this is pointing out this red here, this orangey red is in in between 550 to 900 kilometers per second. So probably in the 600 to 700 kilometers per second speed, versus a slow solar wind, which you'd see in the blue here, is more closer to 250 to 300 kilometers per second, which is usually what we see on a day-to-day. So if this was to rotate, so the sun rotates from left to right when we're looking at it. And so as this keeps approaching the right side here, we would usually get magnetic connectivity at Earth. And so what I mean by that is basically those magnetic field lines on the sun stretch out and they can connect to various points in the solar system. And so in this case, as this rotates, we would eventually start seeing that fast solar wind here at Earth. And with that, that strong solar wind can usually drive, as well as coronal mass ejections, can drive geomagnetic storming. And so if you haven't seen the Northern Lights before, it is incredible. As we were talking a little bit earlier before we started the stream, I recently got to see my first aurora. I actually put in a little picture of myself seeing the aurora for the first time on a drive back from a friend's wedding. So I saw them in Minnesota. There's actually a group that's called Aurorasaurus. They are a volunteer group that does citizen science. They're partially NASA-based, partially citizen-based. And so Aurorasaurus is kind enough to let me do a guest blog. And so there will be a vlog out regarding my trip seeing the Northern Lights with some more pictures in there as well. But Aurorasaurus allows you to report the Northern Lights wherever you see them, whether it's Northern or Southern Lights. You can report them to their website and then they can use it to do science with it. But that was kind of a side topic. So in this case, with geomagnetic storming, we have a KP index, which is a planetary index. So like I was talking about how on Earth we have indexes for tornadoes and for hurricanes, we also have indexes for solar flares and then for geomagnetic storming. And so with geomagnetic storming, we have this index where basically you have G1, G2, G3, G4, or G5 storming. And in May, we reached G5 conditions, which is the first we've reached in, I think, a solar cycle or two. But the one in August, we reached G4. So we had a KP of 8, so a planetary index of 8. And so the planetary index is, I believe, based off of magnetometer data from multiple sites across the world. And so basically, as we're getting an impact to Earth from what the sun's been emitting, whether that be a coronal mass ejection or if that is the coronal whole high-speed stream, that influences how Earth's magnetic field or its magnetosphere, its little protective bubble, interacts. And so as we're getting those arrivals, we end up seeing sometimes a little bit of compression in the Earth's magnetic field or magnetosphere. And basically that can end up leading to a magnetopause crossing. And so, oh, that's unfortunate. I think that's also a video that's not going to play. Dang. So modeled magnetopause crossings usually are seen. Basically here we've got this plot where you're seeing a lot of points, a lot of data. And basically in this image over here, which if it was running, although I'm wondering if it actually has another image. I think I do. Just kidding. Yeah. So we can see here that basically this is the modeled magnetopause. And so that's the front of our magnetic field, our little magnetic bubble. And so this, when there's an arrival, can get compressed and get closer to Earth. And so Earth is in this bubble, and you're looking at this from a top-down view as well. The white is basically showing you the day side, and the black is the night side. So this is, the sun would be over here. And so we're getting material pushed to us this from right to left in this case. And so we can see right here, we're well far away from this dashed line. And this dashed line represents geosynchronous orbit. And so we've got 2 missions that are in geosynchronous orbit, which are the GOES missions highlighted here, which you can see will sometimes move around along this synchronous orbit. But basically, as we get arrivals, we can sometimes get this compression. And so you can actually see this gets pushed in, and sometimes we'll end up getting this magnetopause crossed into geosynchronous orbit. And so we'll see that dashed line here, and you can actually see that we had an arrival that caused this to drop below geosynchronous orbit, which is something that we notify NASA missions about as well, so that if they need to know, basically, if there's a possibility that this compression could cause what's called satellite drag, they can do something about it. However, that's not something we have to worry about personally on my team. We just let NASA missions know that basically there was a modeled magnetopause crossing, and then if they need to do any mitigation with their satellites, they can. And then additionally, around Earth, we have what are called radiation belt enhancements. And so here you can see a diagram which is related to the Van Allen radiation belts. And so this was showing the Van Allen probes A and B basically being launched from Earth to prove that these radiation belts existed, and that was proven. And so basically when we get these arrivals, because the sun has charged particles, as it gets close to Earth, those charged particles will transfer to that magnetic field around Earth, and this includes the radiation belts. And so that can actually charge the radiation belts, and we'll end up seeing that in the data from the GOES spacecraft. And so this is also from the GOES spacecraft. And this is electron data. And so basically we're seeing this is what it would normally look like when we don't have anything going on. But then if it gets charged up, we can actually end up getting elevated values. And so from NASA's missions, we notify them to let them know that the values have gotten high enough that they should know about it is when it reaches the 1000 PFU threshold. So in this case, that's around this line here. So we just briefly earlier this week had a radiation belt enhancement is what we would call it. But as you can see, it dropped pretty quickly after that. And then we've had a little bit of higher values again, but for the most part, it's been pretty low due to how much activity we've had from the sun. And so this is kind of the end of the explanations that I was going through, but in an ever-growing technological world, space weather impacts us all. And so the causes from the sun that we can see is sometimes radio blackouts through changing the structure and composition of the ionosphere, which the ionosphere is one of the layers on Earth, in Earth's magnetic field or in Earth's atmosphere and whatnot. And so we can get sudden ionospheric disturbances from that. X-ray and EUV emissions lasting minutes to hours from that. We can have radio impacts. So one of the ones that I learned about when I was first learning about space weather was how the sun's eruptions can impact GPS signals. And so sometimes you may be driving down the road and your GPS starts acting all wonky. It's possible that it may be just your phone acting up, or it could be that we're seeing some interference from space weather. And then additionally, we can see that radiation is impacted to airlines. So a lot of the US Air Force has their own space weather group. They like to know what may be going on so that they can ensure that there's no problems with being able to talk to their flights. This also happens with regular flights. So if you maybe were originally supposed to have a polar flight, maybe you're flying from like the US or Canada and you were going to fly over the northern pole to go over to Russia or something, your flight may be canceled or redirected if there is enough going on space weather-wise, because basically they need to make sure they can communicate to the airline. And if they lose connection, that can be problematic. So sometimes that can be caused by space weather. And then there can also be damage to spacecraft's electronics. This is very important. And so on our team, I know that we sometimes get anomaly requests. And so basically some satellites may experience an anomaly where their spacecraft didn't work as expected, and they'll ask us to look and see if there was anything going on space weather-wise that may have caused any of those issues. And then the more intense storms can actually cause impacts to the power grid. And those are one in like a million. It's very rare to get those events. They do happen, but there's a lot going on in a lot of governments around the world that basically, like our government in the US has an action plan called the Space Weather Action Plan for what to do if there was a major detrimental space weather event to the electrical grid. And so this is one of the many things, but it's not something that the everyday person really has to worry about. I would say most people who know about space weather, they just are hoping to see the northern lights. But for us at the Moon to Mars office, we like to know what's happening so we can notify multiple missions. And so this is just one of the models we use that shows it's got a CME, so one of the coronal mass ejections. That's what that bubble is that you're seeing go out there. This is modeled into a background solar wind. So this is a movie mode of the version of one of the images I showed you earlier. So the sun is in the middle here. We've got Earth to the right here, and then the multiple missions that we notify. And so that includes the Stereo Head spacecraft, which is one of the spacecraft that is a solar mission. So it looks at the sun and gives us imagery for measuring these coronal mass ejections, along with the SOHO spacecraft. Stereo Head is actually one of a twin spacecraft, but unfortunately its twin did not make it after it crossed the far side of the sun, and so it's still orbiting the sun. However, we do not have connection with it. We lost connection to it. There is the very well-known among the solar community, the Parker Solar Probe mission, which this mission, as you can see, is approaching the sun. It's actually one of the missions that is trying to touch the sun. So it's getting the closest we've ever been to the sun. It's flying, I think I can't remember how close it is, but it's flying very close to the sun. And basically it's touching that outermost layer of the sun's atmosphere, the corona. And so it's been doing flybys. It's basically, it approaches the sun and then it uses Venus, which is in the green dot here, as a gravity assist to keep getting closer and closer to the sun. And so it's actively currently, this is an older run, this is back from June, but it's currently, Parker Solar Probe is doing one of its passes of the sun currently. So it actually, when we run these simulations, it goes inside this circle here. So it's going within that 21.5 solar radii point there. And then one of the other missions we look at, so this orange diamond back here is the Lucy mission, which I believe is on its way to one of the planets, but I cannot remember its full mission at this point. Osiris is the black diamond up here, and that is the mission. So Osiris is an extended mission at this point. When we first added Osiris, it was called Osiris-Rex, and it was the mission that went to, I think it was Bennu, the asteroid, and it took an asteroid sample and gave it back to Earth, and now it's on another mission to another asteroid, I believe. So now it's called Osiris Apex. So its mission got extended and is doing another mission now. So that's very exciting with that one. And then Mars is up here, which we have a lot of missions by Mars. And because we're hoping to get humans back to Mars, there's definitely a lot of focus on events headed towards Mars. And then we have Mercury, which I don't know that there's a mission there currently. There might be, I think actually Bepi Colombo, which is an ESA mission, which is this yellow diamond down here, is now connected to Mercury. I think the two of them are going together. And then this red diamond up here, not to be confused with the red square, this red diamond is Solar Orbiter, which is also another mission headed to the sun that will be observing the poles of the sun. And so this is a very complicated thing to explain, but basically you're looking at a top-down view of the sun, and then you can see that Parker spiral happening from the sun's rotation. There's a lot of information in here, but usually what we look at is how this bubble, where it hits. And so we can see that there may have been an Earth-related impact with this one, and I do believe we saw an impact at Earth and had a little bit of an impact here at Earth. I don't think it was that serious or anything. And then we could see that it was possibly going to have a glancing blow to Mars here. And then Parker Solar Probe may have seen it, and Stereo Head likely saw it. And then even Lucy, I think, saw this one. So this was back in June. This was that CME that I showed you in that video. This is what the modeled result was. And then from this view, you're looking at the same model, but instead you're looking at Earth from the side. So if we were to rotate this and look from the side, we could see Earth, and then this gives you an idea from if the CME is traveling more above Earth or more below Earth. And then this one is probably the hardest to explain on the far right, because it's basically following along this line here. It's kind of like if you were to take a paper towel roll and unroll it. You basically have from north 90, south 90. It's like the combination of this view wrapped all the way around here, unrolled. I'm not sure if that made any sense. It's a very hard one to grasp and explain. But these are just some of the missions that we had. And so with this model tells us, it can usually tell us when we expect to have an impact at Earth. And so it was modeled to impact Earth back on June 10th of this year, around 14 Universal time, so Zulu time, 1400 Zulu time. And it actually ended up hitting within 2 hours of that is what we saw the actual arrival.
Karina?
Yes.
On those charts, that's a wealth of information for sure.
Yes.
Are those saying that they're predictions? Are there websites that show this in real time or close to real time?
Yes. Yep, there is. And I can show that at the end of the slides. I can open up that website and show you.
All right. Thank you.
Yeah. And so this is just some of the missions that we work with. And so we can see that there's a plethora of them, but this is definitely not all inclusive. So we've assisted with some Mars-related missions, which includes MAVEN, and then the Mars Perseverance and Ingenuity rover and helicopter, OSIRIS mission when it was REX, and now we're assisting it with OSIRIS Apex, the Artemis missions, which is the next set of missions to send humans back to the moon and then to Mars. I know that I think the next launch is supposed to be no earlier than September of 2025. And that will be a crewed mission. There's already 4 astronauts selected to go at least in orbit around the moon and then come back. And then Artemis 3 is when we'll have boots on the moon again, which I think is no earlier than 2026. The Space Weather Prediction Center at NOAA, we collaborate with them very, very much. They are the official forecasters for space weather for the US. So if you want any official information on space weather forecasting, it should come from NOAA. LASSOS group is one of the groups at Goddard who we work with to identify what's going on in the near Earth environment for arrival signatures. Solar Orbiter, as I mentioned before, is one of the missions going to the sun. Parker Solar Probe is a mission to touch the sun, as it says on their logo. The James Webb Space Telescope, we assisted them with their launch. We gave them space weather support for that and continue to give them space weather support with just a general space weather report every week. Solar Dynamics Observatory, we use them to observe the sun. Same with Solar Orbiter, Stereo. And then the Space Radiation Analysis Group, which is at NASA's Johnson Space Center in Houston, Texas. They're the ones that get to communicate directly to the International Space Station, or the ISS. We communicate with them on the solar energetic particle risks. We have tag ups with them basically every day of the week. And then the Community Coordinated Modeling Center, which is at NASA as well, they are the ones that host a lot of the websites we use that we populate. So a lot of the online catalogs, which is what I'll show you to show those real-time results. But with that, this is just a nice little view of our team. It's a relatively small team, but we've grown quite a lot. When I joined, there was only 4 other people on the team, so I was like the 5th person to join. And so it's really nice to see how much our team has grown. And you can see that we do a plethora of things. We've got analysis is the main thing of, as you can see for most of these folks, but then there's some scientific software development, there's anomalies. We've got a James Webb Space Telescope support lead, validation support. And so it's just kind of, and training, we have training that we do on our team. Usually when we hire someone, it takes up to 6 months to train them to do the job. So it takes at least half a year. And so we have one person who's dedicated to doing that, which is absolutely crazy. But they do such a great job. But so that's where I would say that I have, but I'd be happy to show you those links. If anybody has any other questions, though, I'm happy to take that as well.
Yes, we have some questions. Please go ahead.
Do you do anything with cosmic rays?
So we don't. I know that there are definitely folks at the Space Radiation Analysis Group who look a little bit more at cosmic rays because that can impact the radiation dosages for those on the ISS. But at least that's my understanding. But as far as our group, my team does not do anything with cosmic rays at this point.
There was another question. Yes.
So is there a way that you can train a generative AI model to look at the sun for you? And if so, what are the hurdles there? And if not, what are the hurdles there?
So, it's a good question. I know that there are definitely a lot of folks at NASA who I've seen who are trying to do AI modeling. It is very tricky. I think the biggest hurdle is just having enough knowledge of what the background is of the sun. So right now, a lot of the missions that look at the sun are in the sun-Earth line, which is not so helpful because the sun is always rotating. And so in order to really get a good AI model, you need to know what's happening on the sun from all points of view, and we don't have that. Versus if you were to do something on Earth, you have a lot of data from being on Earth to be able to look at, okay, can I make a model from all of these points on Earth where I could get measured data? So it's very hard with the sun in order to be able to do that because of the lack of visuals on the sun at this point in time, and then just not having enough in situ data in order to do that. It's another good question.
Thank you. Are there any other questions here from the observatory?
I have a question.
Okay, go ahead, John.
Outside. Actually, I don't know if you would know, but when you give your reports, is there something that they do with the probes that for those moments where this blast of solar flux is passing by that they can harden it, or is it just sort of hang on to their hat? And also, second question, what do they do in the ISS?
So both good questions. The first one, so I don't know for sure what every mission does. I think each mission has their own set of criteria. So we can provide basically thresholds based off of what the Space Weather Prediction Center has for thresholds, but there may be certain missions that have different thresholds. So we do have missions where they just want to know if there's anything headed their way. They may not need to do anything. So Parker Solar Probe is one of those missions where we tell them no matter how fast or how slow a coronal mass ejection may be headed their direction, we let them know that there's something headed their direction because it's a science mission. So they want to know if they can observe it. So that's one thing. So they're making their own catalog of events so that they can basically see when they get the data back if they caught the CME or whatnot. If with the fluxes, so the solar flare fluxes, when you get a solar flare, it usually takes about 8 minutes from when you see the flare before you get the light emission from that. And then the particles can take anywhere from, I think it's as fast as like half an hour-ish to a couple hours. Versus when a coronal mass ejection erupts, usually you can see it, and then it's going to take at least a day up to 3 or 4 days to arrive at its location, usually at Earth. It's that, or at least that distance, it's usually about 1 day to 3 days, 3 or 4 days. So when it comes to seeing those flux levels and whether or not there can be mitigation from it, it's very difficult in terms of X-ray flux to have a quick enough mitigation, because usually even with a little bit of heads up, it's only a couple minutes usually. So I'm sure there's missions that do something, but I don't know fully what. In the case of the ISS, when there's a solar flare or there's geomagnetic storming, anything that could be increasing radiation risk, typically that's something that the Space Radiation Analysis Group will notify the flight surgeon, dedicated person, to let those on the ISS know if they need to shelter or whatnot. Typically there's spots, I believe, on the ISS that are more protected. They just have more layers of protection where they can go if it's a severe enough event that they need to protect themselves. Otherwise, most of the time they don't really have to worry about it. The time where it's the most concerning is if they're doing a spacewalk where they have no protection at all. So if they're outside of the spacecraft, or if they're outside of the ISS and they're trying to fix something on the ISS, or they're doing any sort of science data or mission or anything, that's when it's most concerning to let them know they need to go back inside as quickly as possible to mitigate any radiation sickness they could get.
Thank you.
Mm-hmm.
Are there any other questions from the folks on Zoom for Karina or anybody here at the observatory? I don't hear any. Thank you very much for a great presentation.
Thank you.
And we sincerely appreciate that. Very informative. Could you show us that link if you have that?
Not yet, but I can pull
Okay.
it up real quick.
Thanks.
So it's one of the CCMC sites. Let me know if you can see my screen.
We can.
So the CCMC has what's called Donkey, which is the Space Weather Database of Notifications, Knowledge, and Information. And on this website, basically, you can search for space weather data here. And so if you wanted to see what happened, so I can look at what happened from whatever dates are available. I think this goes back quite a bit far, but if you want any of the Moon to Mars catalog data, that's from 2020 and forward. So we can look at what just happened in the last week, and basically by searching, I can see all of the solar flare information, if there's any coronal mass ejections. And so this is a very detailed catalog with all of the measurements. And then if there was any arrival signatures and where, if there was a radiation belt enhancement, what it was associated with, if there was any coronal hole high-speed streams, and then at the bottom here is the latest model runs, which are usually associated with the CME that was embedded in the model run. And so we can see the last one that we had a CME that was worth simulating was back on the 27th.
Okay. Has the sunspot cycle, 7-year sunspot cycle, had any impact on your analysis, your data that you've been collecting and observing?
Yeah, so I didn't even think to add information about the solar cycle. So the sun does have an 11-ish year solar
11 years,
cycle.
I'm sorry, I said 7.
No worries, no worries. It's 11-ish. It's not exact, but it's 11-ish. And so it like indirectly impacts us in the sense that when you start reaching those peaks in solar activity and those higher you have more sunspots on the sun, you have a better chance of having more activity. So indirectly, it will give us more work. But if you have less activity, you know, there's less to do. So right now we're actually in solar maximum. So we're in that peak period. I don't know that we've technically reached solar max yet. I don't think they can say that you've reached solar max until you're actually out of solar max and you've seen a significant decline from solar activity and you've been out of it for a while. So, but we do know that we're at least approaching or in solar maximum at this point. So we're in the height of solar activity that we're expecting to have, and we expect to be in that situation at least for another year or so.
Excellent. Well, thank you very much. We
Yeah, no
appreciate you
problem.
presenting this evening. A round of applause for her.
That was great. That really
Thank you.
was.
Thank you, Karina. Hugely informative
Yes.
is the
Yeah,
understatement.
hopefully it wasn't too much information. I think that's
No,
the
it was
hardest
great.
part
No,
about
no,
space
that's right.
weather is that it can become information overload very quickly.
I'm glad you're there to watch after us.
Oh, it's so much fun. And like the other sites we get to use, we get to look at imagery. Like this is what I would do all day. We would just look at the sun in all these different colors and it would be so much fun. And then we look at all the timeline data and whatnot. So it's a lot of fun. There's a lot to look at.
Yeah.
Great that the technology is there. It's come so far along. It's incredible.
Yeah. And I mean, it's incredible. Like the Parker Solar Probe mission is one of my favorite missions at this point because it's just so impressive that the heat shield on it works so well that I think it actually works a little too well, where they have to heat up the stuff on the other side of the shield because it does such a good job of protecting from the sun's heat that all of the electronics on the other side have their own heating system to make sure they don't
Can you
go
imagine
freeze
that?
from space, which is crazy.
You're that close to the sun and you need electronics to heat it up.
Yeah, it's crazy.
Amazing.
It's actually impressive.
Well, thank you again. We appreciate
Thank you very
spending
much.
time with us this evening.
Yeah,
And
thank you
all
so
for joining
much.
us.
Thank you.
All right, thank you. Have a good night. I'm going to end our meeting now. Thank you all.
Thank
Bye
you.
now. Thanks, Karina.